So, welcome to today's session. In today's session, we are going to see a design of slab. So, the given problem is a hall in a building with clear dimension 10 meter cross 4 meter is to be provided with a slab supported by 300 wide beams at the ends. The floor need to support a live load of 3 kN per meter square, partition load of 1 kN per meter square, and finishes load of 1 kN per meter square. So we need to design the slab by using M20 grade of concrete and Fe415 grade of steel. So the first step in every problem is we need to write the given data. So first one is given data. So what are the given data? We know the size of the slab. That is the size of the slab is. So first given data is size of slab. So the size of the slab is 10 meter cross 4 meter and it is going to be supported by support 300 beam and it is going to support a live load of 3 kN per meter square and it is going to support a partition load 1 kN per meter square and finishes load 1 kN per meter square, and we are going to use M20 grade of concrete and Fe415 grade of steel. So the first step in solving every problem is we need to write the given data. So by knowing the given data, we will give what we need to do because it will create an idea what we need to do. So next step is we need to find out the basic dimension. So before going to the basic dimension, we need to find out what type of slab it is. That is whether it is one-way slab or two-way slab. So we know that in order to calculate the one-way or two-way slab, we know the condition that is Ly by Lx. Ly represent the longer side and Lx represent the shorter side. So here the longer side is 10 meter and shorter side is 4 meter. So if you give, the value will be 2.5, that is greater than 2. So we know that if Ly by Lx value is greater than 2, then it is one-way slab. If it is less than 2, that is Ly by Lx is less than 2, then it will be two-way slab. So here in this problem, the given slab size is, when we are calculating Ly by Lx, we are getting 2.5, which is greater than 2. Therefore, it is one-way slab. So next step is we need to find out the depth of the slab. So here, in order to find out the depth of the slab, we know that from IS 456 page number 37, we have the condition L by D equal to some ratios. That is, those values will be based on the support condition. Here in this problem, they have been given what type of support they have provided or we need to consider. So if the support is not provided, we can assume it is simply supported. Assume simply supported. So if it is simply supported, then the L by D value will be 20 as per page number 37 of IS 456. So here the length we need to take the shorter span, that is 4000 divided by D equal to 20. So the effective depth D is equal to 200 So for slab we can assume a cover of 20 Therefore overall depth will be capital D equal to 200 plus cover, that is 20 So we get 220 So these are all the basic dimension of the slab. Next we need to calculate the what will be the effective length. So we know the formula for calculating the effective length, as we have already discussed in the beam. Effective length equal to clear span plus D, that is effective depth, or we can take L plus support. In codebook, if you see, it will be given as center to center distance between the support. So center to center means clear span plus half of the support on the right side and half of the support on the left side. So I have taken it as support. So L plus D. So L is 4 meter, 4.22 meter, or I can take 4.3 meter because the support which they have given is 300 and the effective depth which 4.20. So effective depth they have given is 200 we have calculated. So we need to take whichever is lesser. So the L effective value will be 4.2 meter. So we have calculated the basic dimension. So next step is load calculation. We need to calculate the self weight of the slab. So in order to calculate the self weight of the slab, we know that volume into density. So volume 1 into 1, because longer span and shorter span we can take it as 1, and the overall depth is 0.22 into 25. So the value will be 5.5 kilonewton per meter square, because we know that for slab the load will be area load, and we have the live load. The live load is, they have given it as 3 kilonewton per meter square, and they have given the partition load. Partition load is also 1 kilonewton per meter square. Floor finish load, that is nothing but the finishes load. Floor finish load is 1 kilonewton per meter square. So the overall load will be 5.5 plus 3 plus 1 plus 1. So 10.5 kilonewton per meter square. This will be our service load. So next step is we need to calculate the design load. So in order to calculate the design load, we need to multiply the service load with the partial factor of safety. Partial factor of safety is 1.5 into 10.5. So the value which we are getting is, it is 15.75 kilonewton per meter square. So we have calculated the load. Next we need to calculate the bending moment and shear force. So the formula to calculate the moment is, because we have assumed the slab is simply supported. So for simply supported, the moment formula is WL square by 8, because it's an UDL load. So moment MU equal to WUL effective square, because here we need to take the effective depth divided by 8. So WU value is 15.75, and the L effective value which we have calculated here, the value is 4.2 meter. So 15.75 into 4.2 square divided by 8. So the value which we are getting is 34.73 kilonewton meter. Next, shear force. Since it is a simply supported slab, so shear force formula will be WU L effective divided by 2. So here 15.75 into 4.2 divided by 2. So the answer which we are getting is 33.08 kilonewton, because it is a force. So we are taking the unit will be kilonewton. Here it is a moment. So for moment the formula is load into perpendicular distance. So unit is kilonewton meter. Next we need to do the check. So we have seen already in the beam, that is we will use the MU limit formula. MU limit equal to 0.138 FCK BD square. Here the F.138 is arrived based on the grade of steel, because the grade of steel which we are using is Fe415. So the value is 0.138. So here we need to check the depth. So D equal to root of MU limit divided by 0.138 FCKB. Here the width of the slab we need to take it as 1000. So MU limit is, here we can take the MU as MU limit. So 34.73 into 10 to the power 6 divided by 0.138. FCK is nothing but M20 grade into 1000. Here we need to take 10 power 6, because here the controlling factor are the factor which is not changeable is FCK, because we know that the value is 20 Newton per mm square. So we need to convert all the values in terms of Newton per mm square, Newton mm. So here the answer which we are getting is 112.175 mm. So this is the depth which is needed for this particular moment, but here we are providing 200 mm. So it is safe. So D required, that is 112.175 mm, is less than the D provided is nothing but 200 mm. So here it is safe. Next we need to calculate the reinforcement. Next step is calculation of reinforcement. In beam we will have two types of reinforcement. One is longitudinal reinforcement, another one is transverse reinforcement. Likewise in slab we also have two types of reinforcement. For a one way slab we have two types. One is main reinforcement, another one is distribution reinforcement. First we are going to calculate the main reinforcement. So in order to calculate the main reinforcement, we are going to use the formula which is available in page number 96 of IS 456, that is mu equal to 0.87 Fy AST D into 1 minus Fy AST divided by FCK BD. So as I already told that for B we need to take the value as 1000. So here mu value is 34.73 into 10 to the power 6, because as I already told here the controlling or the limiting factor is Fy and FCK, which will be in terms of Newton per mm square. So I am converting all the values in terms of Newton per Newton mm. So 0.87 Fy, that is 415, into AST, which is the unknown, and we know that the depth of the slab is 200, effective depth is 200, into 1 minus Fy is 415, AST is unknown, divided by FCK is 20, B as I already told we need to take it as 1000, and D is 200 mm. So by using calci we need to solve this, and we will get the value of AST as, so AST value is 501.51 mm square. So we need to check this value with the limiting, that is we need to check whether it is enough or we need to provide the minimum reinforcement, because for slab we need to check the condition. Main condition is whether the calculated reinforcement is more than that of the minimum required reinforcement. If the calculated reinforcement is less than the minimum required, then we need to consider the minimum required as the actual reinforcement of the slab. So here in order to calculate the AST minimum, the formula is 0.12 percentage of cross sectional area of slab. So here the cross sectional area is nothing but B into D. Here 0.12 divided by 100. B is as usual we need to take it as 1000, and D value is we need to consider the overall depth, that is 220 mm. So the minimum reinforcement is 264 mm square. So here if you see the AST which we have calculated based on the moment is 501, and the AST minimum is 264. So we can consider the AST actual value for the calculation of main reinforcement. So the AST which we have calculated is AST equal to 501.51 mm square. So next we need to find out the spacing, because here if you see the dimension of the slab is very high comparing to its depth. So we need to calculate the spacing. So we are going to use 10 mm diabar, and in order to calculate the spacing the formula is spacing equal to area of 1 bar divided by total area into 1000, because we are calculating spacing for 1 meter only. So here the area of 1 bar is pi into 10 square divided by 4 divided by total area is 501.51 into the value is 1000. So here the spacing value which we are getting is 156.6 mm. So for spacing we need to consider the value which is lesser than this only. In beam we have told that for a longitudinal reinforcement if we are getting 3.1, then we need to consider the round it up to the next value. But while calculating spacing we need to round it off to the next lowest value. That is here if you see we need to provide, let us write as provide 10 mm diabar at 150 mm center to center spacing as main reinforcement, because in slab we will provide the main reinforcement between the shortest span, that is between 4 meter. For the 10 meter we need to provide the distribution reinforcement. So next one is distribution reinforcement. So in order to calculate the distribution reinforcement, we need to use the value AST minimum. So here the AST minimum which we have calculated is, if you see here, AST minimum which you have calculated is 264 mm square. So I am going to take that value as actual value. So AST, please remember this, AST minimum will be considered for the distribution reinforcement. So it is, the value is 264 mm square. As usual I need to find out the spacing, so I am going to use 8 mm dia bar, which is the smallest dia bar available in our local market. So spacing S, it is represented by S. Area of one bar, that is area of 8 mm bar is pi into h square divided by 4 divided by 264 into 1000. So the value which we are getting is, so 190.4 mm. So we can provide 8 mm dia bar at 180 mm center to center spacing. So next step is we need to calculate, or we need to check it for the shear. So in order to calculate the shear, that is we need to check the shear. So first step is nominal shear stress, the formula which will be given in our codebook in page number 72, VU divided by BD. So here the VU value which we have calculated is, here if you see we have already calculated, the value is 33.08 kilonewton. So 33.08 into 10 to the power 3 divided by 1000 into D is 200. So the value which we are getting is 0.165 Newton per, 0.165 Newton per mm square. Next step is we need to calculate the percentage of reinforcement. That is percentage of main reinforcement. Percentage of reinforcement, that is PT equal to AST divided by BD into 100. Here either we can use, into 100. Here we can use either this value or the depending upon the spacing. I am going to use it based on the spacing, that is AST. The value is pi into 10 square divided by 4 into, for 1000 mm spacing I am going to provide 150 mm spacing. In 1000 mm I am providing the rods at 150 mm spacing. So here if you take 1000 divided by 150, we will get the number of bars in that particular 1 meter span. Divided by B is 1000, D is 200. So the value which we are getting is, so into 100, so the value which we are getting is 0.26 percentage. So based on this we need to calculate the design shear strength of concrete, which will be available in the page number 73 of IS 456. Design shear strength of concrete, tau C equal to, tau C value is, for 0.25 for M20 grade of concrete the value is 0.36. So for 0.26 the value is 0.365 Newton per mm square. So here if you see the tau C value is greater than the tau V value. So tau C is greater than tau V, therefore it is safe. So next step is we need to provide the reinforcement detailing. Here if you see in this diagram I have given the reinforcement detailing for one-way slab. So in shorter span we will provide the main reinforcement, that is nothing but this is our main reinforcement. So it is 10 mm dia bar at 150 mm center to center spacing, and this black dot represents the distribution reinforcement, that is it is 8 mm dia bar at 180 mm center to center spacing. So here if you see in the main reinforcement, that is along the shorter span only we will provide the cranking, and in the distribution reinforcement along the longer span we will provide the distribution reinforcement. The distribution reinforcement will be represented by the straight line. So this is the reinforcement detailing for one way slab. So if you have any doubts, please contact me or comment, put comment in the comment section. Thank you.